wants me to use the microphone. Welcome to the ATA. Good to see some good numbers here. So we've got consultants from Frazer-Nash. I met Marc at a mining conference, actually. Yes. Yeah. So we were having a chat, and I heard about Sundrop Farms, and I said, come along and have a chat to us. So Marc's here with Anthony, and they're going to tell us about Sundrop Farms. So I'll hand it over to Marc. Okay.
Thanks for having us along. It's our pleasure to come and talk a little bit about Sundrop Farms. Understand that Sundrop themselves are a little bit difficult to tie down and get to talk about this stuff, but they're pretty happy for us to talk about it, and with their kind permission, I've got some pretty good slides here for you, hopefully. Despite the fact that we are an engineering consultancy and we're pretty technically minded, we've tried very hard not to get too technical in this particular slide pack. I'm conscious of the fact that not everyone's an engineer. So if I can ask that if you've got questions, especially those of a technical nature. Could you hold the microphone, please? Can you hear me now? Is that better? Yeah, cool. I can't quite hear it, yeah, okay. So what I was saying was, if you've got any questions of a technical nature, if you could maybe leave them to the end. I've got one of our engineers here who's much more capable than I am of answering technical questions, so it's probably the better time to do it. So what we're going to go through is a little bit about who we are, which will hopefully give you some context as to why we're standing here talking at all, a little bit about what we do, and a little bit of why we're here. And hopefully that's going to make some sense to you as we go through this. So who are we? So we are a systems engineering consultancy. We provide technical advice in various industries, from defence through renewable energy, conventional power. We've done some work in the oil and gas industry. We do quite a lot of mining. In effect, we're not really a design consultancy as you would recognise it. So some of you would be familiar with the Jacobs and the Orcons of the world. We don't quite look the same as them. We're a little bit more deeply into the first principles engineering. So about 30% of our workforce have PhDs, and they sit within that really high level computational fluid dynamics, FEA type analysis. We certainly do a lot of work across the sustainable and renewable industries, and I'll talk about that a little bit further, but we're a reasonable size. We've got about 700 employees, but we are predominantly based in the UK. So there's about 700 there, there's about 50 of us based here in Australia, but we can use that engineering expertise, and we're very competent at connecting those dots and using project teams from across and from overseas. So to try and give a little bit about what we do, we've got a pretty wide spread of disciplines. So we have, you would recognise, electrical engineers, civil engineers, structural engineers, all of the usual suspects. But it's how we use that resource that's key to how we actually do our work and how we solve our clients' problems. So something we're very good at is defining the problem. So we do a lot of work around capability definition and requirements. We're certainly very good at understanding the problem, and that's even hugely complex problems, and trying to give a little bit of clarity using analytical engineering and computational modelling. We can then integrate solutions much more effectively across different disciplines and provide assurance, which includes safety assurance and environmental assurance, so as that the solutions that we do provide are going to be fit for purpose. One of the things that we do a lot of is due diligence, which is, in other words, taking other people's work and checking to make sure that it is as per the objectives that have been set. And that's probably the area where it's going to add most context with what we've done for Sundrop Farms. So we've been involved with Sundrop since 2013. That started because when Sundrop were looking at developing what at that time was a pilot project into what we know now to be the major 20 hectare greenhouse, they really needed to provide some evidence to their lenders and to the people who were going to buy the tomatoes that this was going to work. Is it feasible? Is it actually going to happen? Are the technical solutions that you've provided going to work for us? So the way they do that is by employing an engineering company like us to do a technical due diligence piece on that design and on that work. And that's how we got involved back in 2013. We did such a good job of that we ended up becoming Sundrop's owners engineers for the duration of the project, and that is still the role that we fulfill. So what we were able to do during that technical due diligence process is provide a lot of feedback to Sundrop about areas where they could improve, where they could do it better, where they could gain efficiencies. And it was through that conversation that they wanted to retain us. Part of the reason why we've gotten pretty good at that technical due diligence is we've done a lot of that work in the UK and here. And in fact, there's a couple of examples here. So we've done work around solar energy harvest predictions. So in other words, what does your solar resource look like? How much sunlight are you going to get? Where's the best place to find that? How do you position your heliostats? Is it better to use PV? Is it better with other methodologies? We've done some work around innovation management for the UK offshore wind accelerator. So something we've been involved in very heavily for the thick end of 10 years now is in the offshore wind development around Scotland and the rest of the UK. Heavily involved in that transition all the way through. And more familiar here, we've been supporting Carnegie with their wave energy device for the last 5 or 6 years, right since they first started, and continue to support them. We do work with clients all the way from the concept stage all the way through life. So we are able to provide a lot of advice around the asset management aspects, so where that feeds into design at the early stages and all the way down through to decommissioning. So I think that's enough about us. What we want to move on to now is the Sundrop vision and a little bit about the feasibility journey. So Sundrop themselves, it's worthwhile pointing out right now, you guys might know this, but there's a bit of a misconception that Sundrop are a renewables business, that they actually have solar as their product, that this is what they do. Well, that's actually not true. Sundrop are farmers. They have a really keen interest in developing farming technology and being able to run farms much more sustainably than they could before. It just so happens that in this particular instance, solar, and specifically heat from solar, is the solution that they found worked best for them. There are other projects that they're currently executing, and solar is not a feature of it at all. They've got other methodologies. So they go to great pains to explain the fact that they are farmers, they are an agribusiness. If solar's a solution, that's great, but they're also looking at waste heat from other streams, other production streams, as other ways of harvesting energy. They certainly recognise that global food demand is about to rise, is in the process of rising. I think it always rises, it's population driven. Climate change is making it increasingly difficult. I understand there might be a few farmers in the audience tonight. I'm sure I'm preaching to the converted here, but it's getting increasingly difficult. Water scarcity is a big issue, especially here in Australia, and in northern South Australia is really becoming a problem for them. The interesting thing is that sustainable farming can be built in inhospitable areas. So it's not necessarily the farming that's the key to this. It's the ability to introduce the solutions to the farming requirement that's the key. Sometimes where traditional horticulture isn't feasible. Where produce is grown hydroponically, you can do it in climate-controlled greenhouse-type facilities, and that's exactly what Sundrop have done in this example. And certainly their view is that sustainable production methods is the future. So just a quick timeline on what happened here. So back in 2010, they opened the pilot farm in South Australia just to make sure that what they were thinking they were going to do was going to work. In 2014, they broke ground on the 20-hectare greenhouse that we are now familiar with. In 2016, they opened the first farm in Europe. And in 2017, they're currently doing another project over in the United States. They continue to find new projects. These are only the ones that we're allowed to talk about. There are at least 2 or 3 others that are in the pipeline right now. So what does it look like? What was the vision? What did they want to achieve? So this diagram actually came after the project was put together. It's just a really cool way of pointing out how they did it. So what they wanted to do was have greenhouses to create delicious produce, whatever that may look like. Tomatoes happens to be the weapon of choice here, but what they wanted to do was be sustainable. So they looked at the sun to provide heat, and they looked at seawater, which was nearby, to provide irrigation and, interestingly, climate control facility in this particular instance. It's worth mentioning at this point that in actual fact, although this is a solar facility, producing electricity from that is not actually the primary concern. It is the heat that they are harvesting here. So electricity production is a byproduct. It's a cogen plant. We're going to explain a bit more about that in a second, but they don't produce electricity as the primary resource and then use that to do everything else. In fact, they only produce electricity when they've got a surplus of heat. Right, this is a lot of words. And because it's a lot of words, I'm actually not going to read it all out verbatim because I've got a better slide to try and illustrate what we did here. But basically, if you want to take a quick second just to read it, these are the things that we do when we're doing technical due diligence. Much easier described by this. So we take a very similar approach to pretty much any technical due diligence piece that we do. And we follow a process called the claims, arguments, evidence. So the idea here is that a particular company, a particular client decides they're going to put some technical piece of equipment together, a plant or whatever it may be. It could be in the renewable space, it could be oil and gas, it could be anything. But what they're doing there is effectively they're making a claim. They're making a claim that they can produce something. In addition to that, they then have to produce some arguments that they're capable of doing that. And then we'll look at developing some evidence that would support those arguments. So the way we break this down is by taking the claims that they're making and actually making sure that that evidence exists and making sure that we can see the path to them actually being able to provide that particular facility. So you can see here along the top there, you can see the claims are defined. So in this particular instance, there was a requirement for an integrated system. Is it feasible? And in claim number 2, the proposed system design is fit for purpose. These are the things that we're trying to prove out. The arguments are developed. So do they have some deeply defined functional requirements? These are some of the things that we looked at as we were going through the process. The evidence and requirements defined. So we talk about requirements capturing skill and experience in technology surveys and mass and energy conservation. So what we're doing is the calculations involved in making sure that what they've said they can do is actually feasible. Once the arguments are supported and the claims are supported, we write that up into a report. So you end up with a piece of paper which goes out to the offtake agreement people. In this case, it's Coles, who wrote up the offtake agreement and actually buy all of the tomatoes that Sundrop grow, but also at that time, the lenders who were going to provide them the funding to be able to do this. So that's where it goes. That's where the technical due diligence piece goes. At this particular point, this is the feasibility side of things. So once we get through feasibility, and given the fact that we already know they've done the project, so we know they've got approvals for that, so they had an offtake agreement and they got funding for it, we moved into detailed design. So in actual fact, what we went on to do was take the detailed design that they created after we told them that everything was okay, and we did technical due diligence on that, and it's a slightly different approach. So you can see here that we need to check the process, so is the correct climate data being used, you know, is the heat balance calculations correct, you know, what do the energy losses look like, how can we optimize plant. We check the design to make sure that it's actually ticking the boxes that we can see required to be ticked. We also check costs, and it's one of the interesting things about us as an engineering business is that we do a lot of work in this economic side, making sure that the costs that you say you're going to do it for actually match up. Is it feasible from a cost perspective, not just a technical perspective? And check the schedule. If you say you're going to do it in 2 years, is it actually feasible? Are you going to be able to buy the equipment in that time, secure your contracts, get out there and be able to do it? So these are all things that we check at the detailed design phase. So again, this is a picture of what the process actually looks like now. And at this point in time, I'm probably not going to go through it in any extreme detail, other than you can see that we've got energy from the sun, and we have a natural resource in the form of the seawater that's pretty close by. The process here results in us being able to grow tomatoes in a greenhouse in a sustainable fashion. We can come back to this later on if there's any technical questions on this, so keep it in mind. So executing the plan. What was the timeline? I've got a few pictures here from construction. the role of the owner's engineer, what happened when we got into that position, and what did the outcomes look like. So we're going to talk a little bit through that. So timeline. So in 2014 is when the funding was secured. That was when they finally got everything ticked. Everybody was happy with what they were going to do. There was a $150 million development contract awarded to John Holland to do the construction, which was over a period of about 18 to 24 months, and they came pretty much within schedule. ProManage were engaged to project manage the construction phase of the project, and in case you're wondering, there is another presentation going on tonight. It just so happens that ProManage are there doing that presentation. Unfortunately, we didn't communicate that particularly well to each other, so apologies for that if you've had to make a decision on where you came tonight. Josh and I will compare notes after this. So in December of 2014 is when construction began. In 2015, Aalborg, who are a provider of concentrated solar power solutions, started the construction of the integrated energy system, which is what we're calling the tower and heliostat system together. The solar tower itself consists of 9 sections. It was actually constructed in 10 weeks, which I think is pretty quick, to be honest with you. It's pretty tall. It's 120 meters of construction, and yeah, it's going to have to sustain itself in pretty high winds and all the other things that are required, so it's pretty impressive timescale. If you consider the structure where the boiler sits is 234 tons, you can imagine there was some pretty substantial lifting around about the construction project at the time. eSolar were contracted to provide the heliostat, so interestingly it was a different company. There was a collaboration between the two, so they're not from the same company. And at the end of, or towards the end of 2015 is when we started to do some testing of the facility. And by October of 2016, commissioning process had been done, and they were cutting the ribbon, which was pretty good effort. So some pretty cool pictures. So just as a bit of a note here, so upon completion of the feasibility, you know, it was time to scale up, and the 150 million saw them build what we see in front of us here, and it was done pretty quick. To give you a sense of scale, I don't think you can quite see it on this one. There is another picture which I've got. There's a picture of a ute down in the corner. It gives you a bit of a sense of how big this actually is, but to give you an indication, from here to here is approximately 500 meters. That's half a kilometre. It's pretty big. That's a lot of mirrors. So just to give you an even better sense of scale, incidentally, this is Ian Watson, who's one of our lead engineers. You can see just from perspective here, it's getting close to 200 meters from where he's standing to the other end of that greenhouse. And a really interesting fact here, you know, so there's 56 bays, and each of them are 200 meters long. So one of the interesting questions we had when we were talking to Sundrop about what happens when stuff breaks down, what happens if your watering system breaks down, their answer was, well, we could send someone round with a watering can. Then you realise, if you do the maths here, and I don't know if anyone's good at maths, but it's 45 kilometres of walking in one of these greenhouses to water every one of those plants. So yeah, that was never going to work. So what's interesting is it actually really helped develop that conversation around backup and making sure that you've got some, you know, backup plans, you've got backup generation, you've got some ability to keep your plant running no matter what. If you lose all these plants, it's an expensive venture, so keeping them watered was really pretty important. Interestingly, there's a ventilation system in here as well, which was pretty specky and pretty new at the time. So again, just to give you a bit of a sense of just how much of there is. So there's fans in there, each of them 0.7 of a metre, 700 millimetres, so about that far across. There's 1,140 of them in each of these greenhouses, so that's a pretty big effort. There was also significant infrastructure outside of the greenhouses themselves, so I'm sure you'll appreciate that there's a desalination process going on here, so there is an outfall. So the outfall comes out at the Alinta facility, so it's about 6 kilometres away from the farm. There were certainly all sorts of EPA restrictions on us as to what we could do there and what the composition of the outfall actually looks like. Just for interest's sake, the salinity of it isn't that much higher. It's not like a desal plant, like the Adelaide desalination plant, which is a factor of about 8 times higher salinity on the outfall. This is only about 25% higher. I've got a nod of a head from a technical guy, so that must be right. About 25% higher than normal seawater salinity. So it's not huge. It wasn't difficult to get the consents for this. The bit that I find really interesting is the fact that it's 6 kilometres away. Please be aware there's no pumps here. It's all gravity fed. So it's gravity that takes it down here. There's a height difference of about 6 metres. And that's how they get it out there. Which cut down on energy costs, which is the real point. So I thought a picture of a day tank would be quite interesting. So there's actually 2 of these. They're both the same size. And to give you a sense of scale, there's a couple of guys standing in there. This is a 1 megalitre tank, so there's 1 million litres in here. There's 2 of them, so there's 2 million litres in these 2 tanks. When it's hot in the summertime, they use all that water. They'll use 2 million litres in one day out there. So hence the reason they've got a desalination process to make sure they can sustain that. That's a lot of water, but then again, it's a lot of tomatoes. Okay, so this is probably a little bit cryptic. What we're looking at here is the base of a heliostat. Now, I've mentioned this word a couple of times. I'm hoping that people have made the leap of understanding. We're talking about the mirrors that point the sunlight up to the tower. So just to be clear, couple of interesting things around this. So we did a lot of work on this because we had some issues around wind shear. What was going to happen when it was going to get windy? Would it move? How were we going to actually make sure that these things stayed down? So I don't know if you can see it very clearly, but there's a pretty interesting pinning arrangement here around the base of this to keep everything where it needs to be. If you consider that there are thousands and thousands and thousands of these things out there, then you understand where we've got to get it right. You don't want to have to go back and fix it every time. The other interesting fact here is that the heliostats track. They actually move depending where the sun is, so that they continually have the highest possible efficiency. But what is kind of cool is also sensors on them to pick up wind speed. And what happens is when the wind speed gets to a certain point, they actually flatten out, so that the wind isn't actually having such a shear effect on the heliostats, so they move into different positions. All right, so owner's engineer. So what I'm going to do is describe a little bit about what the owner's engineer role is, as per the slide here, and then I'm going to pass on to Anthony, who's going to give you a couple of examples. So effectively what we were engaged to do once we got through the process of technical diligence was to provide independent advice. So you can imagine John Hollander out there, they're constructing away. There's always issues that pop up. There's always issues with design. It never is easy. You know, you've got to interpret drawings. You've got to understand what you're trying to build. There are often complications when you get out there and actually start building stuff. So our role in this was to provide that technical backup. So we effectively acted for Sundrop Farms as their engineers so that we could answer those questions when we came through. So we actually worked very closely with John Holland in that regard to help them solve the problems that they were seeing, or to help Sundrop make decisions around, do we throw some more money at it or not? It's effectively what we were there for. So assistance in reviewing designs and specifications, evaluation of engineering solutions and variations. There were a couple of things that cropped up that are a little bit interesting, so I'm going to pass you on to Anthony, who's going to talk about it in a bit more technical detail.
Thank you, Mark. I'm going to give 2 examples. They are both thermodynamics examples because that's my area, and we've done a lot more than just thermal fluid heat transfer type of work. And but the first one here, we're looking at the irrigation and the multi-effect distillation, which is what they use to desalinate the water, provide the water into a freshwater lagoon. That lagoon is about 25 million liters big, and the distillation provide about 85% of the water that Sundrop needs. But they also have assay water provision if they need to, and during the peak summer period, they will need some water from assay water, and so these 2 are the main supply to the freshwater lagoon, and then the water goes into a sump, which then got pumped up into a day tank, and before it gets into the day tank, it gets treated with UV filter, etc. And the day tank, as Mark mentioned earlier, will store the water for the irrigation, and it can store up to 2 million liters per day. And with this operation, the grower of Sundrop, what they like is that for the irrigation, they want the water to be about 18 Celsius cool in peak summertime to optimize the plant growth. And we look at the data. The multi-effect distillation normally gives you the freshwater outlet sort of a few degrees above seawater, because seawater is the final stage that used to cool the distilled water. And SA water also, if you open your tap in the summer, you'll find out how hot the tap can be. And as a matter of fact, both of these can reach above 30 Celsius. So we did some calculation, taking into account all the heat transfer, the global horizontal irradiation, the wind chill effect, and the heat of water going in, the heat of water coming out, etc. And no surprises, we found that the water irrigation temperature coming out is significantly higher than 18 Celsius. So what the decision is that they need to add a chiller. And with this model that we have, we help Sundrop to derive the chiller. And first of all, we need to size the chiller to find out what chiller sizing would allow them to irrigate at 18 Celsius, given the water inlet temperature. And secondly, to also find the chiller position. Where do you put it is the best. We look at consideration of putting a chiller before the day tank and after the day tank. And the fact is that they only need irrigation for a few hours a day. And if you imagine you need to cool that water in immediately, where during the irrigation you have to cool quite a lot of water at peak irrigation rate. However, if you cool the water before the day tank, you can actually effectively cool it 24/7, gradually fill up the day tank, and then the next morning you start irrigating. And one thing we found is that even the paint on the tank actually affects the heat transfer by quite a lot. So how much heat gain of the tank during the day is quite significantly affected by the surface finish on the outside. And if you put the chiller before the tank, you actually lose a little bit more energy than if you put it there. So you have, because the tank actually absorbs a bit more energy when it's actually kept cool most of the time of the day. And so the compromise is that you can have a lower capacity chiller, but you actually use a little bit more energy, or you need a high capacity chiller, but you actually use less energy in chilling the water. And the solution is that using the lower capacity is actually much better. It gives you also the opportunity to actually chill it for different time of the day, and etc. And so that was the solution that we derived for Sundrop. And next example is the thermocline tank. And I'll start by the conventional way of storing heat with water. Normally you have a cold tank and a hot water tank, and you store your cold water in one tank, and then you use some means of heating up the water and put in the hot water tank and use for heating or any means, etc. The thermocline tank is a technology that uses the property of water, that hot water flows above cold water. And the benefit of that is that you only need one tank. And so you keep the hot water above the cold water all the time, and because it flows above, it's less dense. And so you only need one tank, and you also need less equipment, and you need less space. And so the benefit is that you have a single tank, you reduce the cost, and with less equipment and less complication, it's actually more reliable as well operation. However, there is a complication, is that Sundrop wants to use the thermocline tank to store the energy all year round. And as you imagine, having hot water directly above cold water, they will start mixing up the hot water. They will smear the temperature. The hot water becomes cooler and the cold water becomes warmer, etc. And so the key thing is that you can't actually operate the distillation very effectively if the hot water gets cold. And so that could be a problem. And in fact, in IRENA, the International Renewable Energy Agency, in 2014 published a report saying that large thermocline tank for seasonal storage is actually not mature technology. And so that represents a risk to Sundrop. And so we decided to do some analysis to see if they're going to invest in these big tanks, are they going to work? Before I go on to what we actually did in terms of analysis, there are two tanks here. You can see this is a 22,000 meter cube tank, and this is 6,000 meter cube tank. The 22,000 cube water tank is used to store the energy that is collected from the solar tower. The 6,000 meter cube tank is the one that they use to recapture the waste heat from the distillation plant. The salt water coming out of the distillation plant is actually still quite hot, so they use a heat exchanger to recapture the energy. So maximize the use and minimize the waste. Basically, that's what Sundrop's philosophy is. And what we did for Sundrop in terms of validating the thermocline tank performance is that we use a state-of-the-art computational fluid dynamics analysis and to simulate what the tank does. And for some interest, the heat transfer between the hot water and the cold water can take place by convection, conduction, and radiation. Thermal energy doesn't travel much via radiation, so that is not a problem. Conduction is actually quite slow. What we find that the smearing effect occurs over months, but the convection, which is the stirring up of the fluid when you actually inject the hot water into the water, which causes turbulence, etc., is the main problem, is the main culprit if you're not careful, and that can stir up the tank by quite a lot. And so what we did is that we used computational fluid dynamics to simulate that mixing effect, and particularly turbulence, and to see how quickly the hot water is going to mix up with the cold water. But the model we have, just in case you're interested, is 5 million cells. So it's a very big model, and it took about 3 days to solve 4 hours of transient of hot water injecting in the tank. So it's not actually quite possible to use that to simulate what Sundrops want to do, which is throughout the year, try to look at whether the tank is going to work or not. And so we use the CFD result and transfer that information into a one-dimensional heat transfer model. And it's a temperature transport equation, basically. And by using that, we can actually simulate the whole year of operating the thermocline tank in a few minutes, basically. And that work has actually been presented in the World Renewable Energy Congress recently in Perth, and it's been reviewed for publishing in a journal. And so at the time we did this model, we simulated the whole year of operation for Sundrop, and our conclusion is that yes, your thermocline tank is going to perform all right. It's not going to mix up the fluid too much so that it's going to cause problem. And at the time when they were doing commissioning, we took the opportunity to try to validate, to see whether how good the model actually agrees with the measurement, with the commissioning data. And you can see here 2 pictures. The top one is what we predicted, and the bottom one is what is measured. The horizontal axis is time, is over 2 weeks, and the vertical axis is the temperature, is the height of the tank. So red is hot, blue is cold. So if you take, say, 15th of May, you get on the top a small amount of hot fluid there, sitting above quite a lot of hot water, cold water, sorry. And as time goes by, they inject more hot water, and then the hot water line penetrates down the tank, and then they extract it to use to heat the greenhouse, and then that goes back up again. So, yep. And as you see, we actually get very good agreement, and so that method, as I mentioned, is now being reviewed to be published in a journal paper. So, and the technology can actually be used to de-risk this high-cost equipment. I forgot to mention is that each of those tanks costs more than $1 million. So if you get it wrong, it can go very wrong, basically. And this method can actually be used for molten salt as well, because the fluid property is actually quite similar to what water is. And I think that's the end of my bits, and I'll pass it back to Mark.
So I found this kind of cool picture, which is a great representation of what it actually looks like out there. It's complete with mountains, but I don't think the ones out there are particularly green, so apologise for that. What I wanted to move on to was a little bit of discussion about the outcomes that they realised out there. I don't know if they knew at the time just what a landmark project this was going to be for the state, but I mean, everybody is talking about it. It's been really great for us, it's been great for them. So I just wanted to establish just a few of the things that they did that were pretty innovative and a little bit different to most. So at the very least, they've achieved water as a sustainable resource. So they actually use seawater to cool the greenhouses. And again, I'm not quite sure, lots of misconception around the fact that everything gets desalinated, it's about producing fresh water and doing irrigation. Well, it's not as simple as that, they use it for more. So there is actually out there some lattice cardboard pads, and they get continually soaked in seawater, so it's very much like your evaporative air conditioning systems that you might have at home. The air's blowing through, it is evaporative, and that provides cooling air when it's hot. But the interesting thing about seawater is because it's full of salt, it actually sterilises the air. So it actually helps act as a natural pesticide as well. So there's a couple of things going on there that's not immediately obvious. So they do use a thermal desalination system powered by the solar tower. So the intake seawater is pumped using solar energy provided electricity, about 5 kilometres from the Gulf, and it comes into the farm's desalination plant from there. Don't really want to get too bogged down in the details here, but as Anthony mentioned already, you need to be aware that it's not all coming from there. We do top up with fresh water. There is a little bit of a mix there. So it's not entirely dependent on salt water. But what it does do is it saves about 300 million litres of fresh water per year by using seawater. So there we go. I couldn't quite remember earlier, but the number is 23,000. That's how many of those mirrors are on the ground out there. It's a lot of them. The tower itself is 115 metres high. So it is an integrated energy system, and as we've mentioned already, the driver here isn't necessarily to produce electricity. The actual driver here is to produce heat, and that's what they use to drive the process. It's quite significant. So they're capturing about 40% of the sun's energy that's coming down onto those mirrors, which is around about 40 gigawatt hours per year of heat storage, or 3 gigawatt hours of electricity generation. So the solar thermal infrastructure itself, it's a closed loop. So it's, according to this, 22,000 cubic metres of hot water is in the storage tank next door to it, and they generate power through a 1.5 megawatt steam turbine. But again, I make the point that that's not necessarily the primary focus of this. So the medium used, and some may be aware of the fact that in a solar thermal system it's often molten salt that they use, mainly because it's very stable thermally, but we don't need that kind of heat. Molten salt will be molten at around about 800 degrees C. In fact, we don't need anything like that. So we use it to heat the greenhouses in winter, and we run a desalination plant to generate fresh water. And the waste heat from the hot brine, as Anthony mentioned, is also captured so that we can use that. So the interesting thing about what we've just explained is that it's actually about balancing out the needs, because it's seasonal. It's not the same all the time. When we've got excess heat and we've got excess power, we will generate electricity and feed that back into the grid. But in actual fact, we don't always have that situation. It depends on what's going on. So through the year, you may find that we need to use more heat to produce fresh water, or you might find that we've got enough fresh water and we can use it to produce electricity. So there's a monitoring system there that continually balances that out and looks at it and works out what's the best thing to do here at this particular moment in time. Interestingly, it certainly avoids a huge amount of CO2. It's in the order of 16,000 tonnes annually. So just going to round this out a little bit about talking about the objectives and the fact that they wanted to grow food sustainably, and a little bit about what we think has made this successful. So the vision they had, what they started with, and what they have actually realised now. So it's a 20-hectare greenhouse. It uses coconut husks of all things. That's the medium which most of the tomato plants are actually planted in. There's a bit of a mix, a bit of a cocktail of nutrients that they sit in, but coconut husks is one thing that actually promotes growth. They use carnivorous insects to control pests. They try very hard not to use too many chemicals out there. They've got sustainably sourced fertilisers and micronutrients, which is part of the mix. They grow in the order of 15,000 tonnes of tomatoes. I got the technical guy to do a bit of a calculation for me here, and just to give you a bit of a frame of reference, it's about 90 million tomatoes. Average size tomatoes, it's a lot of tomatoes. All of them go to Coles. Coles buy them all. There's one offtake agreement. Technology ensures optimal climate conditions for plants, enabling year-round production. So their yield is between 15 and 30 times higher than a normal farm that would do this, mainly because all year round they've got a controlled environment. They don't need to worry about the seasons. It's a completely closed loop. So they certainly did what they said they were going to do. We wanted to give a little bit of an opinion on this because obviously we've been involved since very early in the project, and we've seen a number of these projects put through. Believe me when I say not all of them are as successful as this. Some have failed spectacularly for the most strange of reasons, but Sundrop really nailed this since the start, and we give a bit of thought to this, and we're trying to work out why. Why is that the case? So we did a little bit of asset management assessment here, and these are the capitals here you see. So value. So Sundrop's assets provided value by being aligned to its objectives. So what we mean by that is that Sundrop focused on the fact that they were an agribusiness looking for an outcome, not a renewable energy business looking for a solution. So they had a problem they were trying to solve. You often find that it's the other way around. There's any number of conversations I've had with really smart people who have got a fantastic solution, if only they had a problem that they could solve with it. It's the wrong way around. So when you have a very clear value here, it often makes things much easier because it helps you to set your objectives. They had great alignment. So Sundrop's objectives were very clearly defined from the start. They were very, very vocal and proactive around this. So they really helped themselves to understand the impact of design decisions. If anyone's familiar with asset management, you'll understand that there's a feedback loop always. When you're in construction phases or when you're in detailed design phases, if you make a change, you need to go back to the earlier phases and have a look at the impact that's going to have. I have seen projects where pieces of pipe don't line up because they haven't made that very simple assessment. A piece of equipment that was ordered because it was $1 million cheaper physically doesn't fit. So the asset management principles of continually monitoring and feeding back change requirements to understand the implications of change were applied and used to assure alignment with objectives. That was driven by them, not necessarily by us. That's a key differentiator. That's a very mature client, even though they were in a mature business. Leadership. All managerial levels at Sundrop were committed to successful asset management. They were all on the same page. They were all communicating. They all knew that we were pulling in the same direction. They sought to understand the reliability, maintainability, and availability of the assets. What was it going to look like when they actually had this up and running? What were the decisions that they had to make along the way? Very proactive in that space. Assurance. Sundrop were able to govern itself effectively and plan for the future and make strategic and tactical decisions. So in other words, matching its assets to its objectives ensured that they were not affected by the vagaries of the weather. So where that manifested itself, I've kind of alluded to this already, but they were very good at making sure they had a backup plan in place. So they knew right at the very start that if they ran into trouble further down when they were trying to grow tomatoes and suddenly there was a weather condition or something broke down, or there was a blackout, who would have guessed that? Interestingly, when that blackout came through, they ran through it. They just kept going. They switched on their diesel backup generators and kept on going. They didn't stop, wasn't affected. So our belief is that that's where they proved themselves to be really successful, and that's why they continue to be successful in the other projects that they're executing right now. So that's kind of where the presentation finishes. I've got some technical help here, as you've probably realised. He's very good at the technical stuff. If anyone's got any questions, happy to take them.
How much electricity do they need from the grid?
The answer is very little. They are grid connected, but generally speaking, the generation capacity they have on site is enough to overcome that. But it depends on the mix, because sometimes it's more cost effective for them to pull capacity from the grid than it is to providing into it. It depends on that balance that I'm talking about. So the answer to your question is very much a moving target. It depends where they are.
I'm interested, you may have said this already, in the freshwater lagoon you had there, and the chiller and the water going for irrigation. Two different questions. How much work do you guys have to do in the temperature? Like, what is the temperature before it goes in the chiller and when it comes out for irrigation? The other question is, how many parts per million comes out of your desalination and the EWS one, and then it goes on further?
So I'll answer the first question first. We actually model the whole thing as a transient. So it's a mass and energy conservation, and the water going into the chiller and coming out of the chiller. But basically that's a coefficient operation. And we select the chiller, and then we decide how good it can work, and then take the heat out of it. And when it draws in the day tank, the energy that is being absorbed through the solar, etc., is also taken into account. So if the water is being heated up in the day tank while it's being set there, it's taken into account. So during the day, when it's being drawn out of the day tank, you get the flow rate out of the tank, and you got whatever from chiller going in, you got the sun coming in, and the program does actually evaluate what temperature the water goes out as they irrigate.
You don't have a preferred temperature for irrigation?
Sorry. 18. Sorry. Yeah. That's yeah. Yeah. In fact, what we found the solution is, I think below 20 would be acceptable. So that's what we did. Yeah.
With greenhouses, the problem, or with glass greenhouses, they tend to get hail damage. How have they prevented hail affecting or breaking the roof when you get a massive storm?
They're not glass. They're a polypropylene. They don't even try and prevent that. The reality is that the cost profile is such that it's easy to replace. They run on a full replacement period of around about 2 years, and that's it. So it's extremely cheap. So if you ever get out this opportunity to go out and have a look at it, the cost of the polypropylene that they've got over the top of this is so low, is that they anticipate replacing it roughly in a 2-year cycle. So yeah, absolutely. Yep. So they don't even try and stop it. They're quite happy for the hail to come through, because from a cost perspective, the damage it will do is relatively minimal, unless it's the big hail that we saw recently, which is a little bit unusual. But tearing the prop, doesn't really matter too much. It's going to get replaced in a 2-year cycle anyway.
So with polythene film in an area that size, I would have thought the chance of it being wind damage would be very
They've got a pretty interesting support mechanism for it. It's fairly elaborate to make sure that it's well supported all the way through. Interestingly, they've used the same concept for most of their projects where they involve greenhouses. The other good thing about that is it's quite easy to construct. So everything's very lightweight, everything's pretty easy to put together. So it's for them, it's as much about reducing cost, but a perhaps unintended benefit is that when you do see damage and you do things going on, it's relatively easy to fix.
massive recycling problem every 2 years.
Yeah. Knowing Sundrop Farms, the fact that they can do it every 2 years and the fact they've allowed for it every 2 years, I can't see that they will do unless there's a significant amount of sun damage or damage to it that they would have to cope with. But certainly in the costings, they've allowed for the fact that they could potentially do that if needed. Yeah.
Probably want to add that the greenhouse was designed by Van der Hoeven from Holland. So they're actually more aware of cold weather than probably people here would be. And I remember looking at the greenhouse design, and they did take into wind loading and, funny enough, snow loading as well. But anyway,
Sorry, can I just take a question?
The data tank looked like a corrugated iron tank, just a very large one. Was that very thick
The day tank. So the day tank is corrugated iron. Was that the final construction of it?
I do have a number on the thickness, but I can't remember, to be honest. What's it? Yeah.
Be a lot thicker than a normal corrugated iron? Because it's such a large tank.
Yeah, I don't know what because farming is not my background, but when we did the calculation, we did have the thickness of it, and so that we can evaluate the heat transfer. I can find out that information if you're interested, and yeah.
Something to remember is it's not the width of the tank that's the controlling factor, it's the height.
Yeah, that's right.
So you can have a base of 2 meters or you can have a base of 25 meters. The actual support mechanism for it doesn't need to be any more substantial, it just depends how high you end up. The higher up you go, the more pressure you're going to find at the bottom of it. But that doesn't change with the width. So that actually isn't a huge controlling factor in that regard. Sorry, so you had a question?
You're obviously heating the water. I'm assuming it's to drive a turbine. What happens at night? You don't need the turbine at night, or you're storing that water energy somewhere, that heat energy?
So the heat's stored within the thermocline. So there's a fairly, one of the interesting things about solar thermal is that not only is it hugely efficient, but because you've got your thermocline tank, you can store power for a very long time. So it actually remains hot all the way through the night. You don't need to stop. Obviously, having said that, it does depend a little bit on time of year, which comes back around to this balance of energy, so when we don't have enough heat there, then we will draw power off the grid to compensate for that. But generally speaking, in the summer months, there's more than enough heat within the tank and within the water there to drive all the things that we require.
What's the lifetime of the system? It seemed to me that heliostats sort of degrade with time and all that sort of thing.
Design life, is that what you're talking about? Design life? What did we design to?
Well, how rapidly is it weathering sort of currently?
Don't hold me to that, but I believe it was 15 years, the design life of the plant. Yeah.
Did you catch that? 15 years. So they reckon that the way the plant operates, it's good for 15 years. And then I would have to suggest that there would be elements of it that would be replaced after that, but that's as an overall effort. Go again. Go.
You talked about house stones and the glass house, but what about the mirrors? Do they get damaged from
Yep,
the stone?
absolutely. And there's nothing else for it. They just got to replace them. Interestingly, so here's another little fact for you actually, because they have an automated system for cleaning the heliostats. So there's a little automated guided vehicle that runs around and actually just does laps up and down all the heliostats. It's got a thing on it that looks like a window wiper, and it goes around and it sweeps off the dust. And it runs all the way around and then it starts at the beginning again and just does that continually, because there's quite a lot of dust being generated out there, as you can imagine. So, yeah. Sorry, go. Good question. What are the mirrors made of?
I think they're just mirrors, actually.
Glass, I guess it's glass. Yeah. Glass.
Yeah.
Yeah. We're going to make a sweeping assumption it's glass.
You mentioned that you're able to use 40% of the sun's
Yeah.
energy out of this. Can you just explain that in the context of what happens to the other 60%?
So if you imagine that the heat energy that's coming out the sun and landing on the farm, that 500 meter square area, about 40% of that is being reflected. Okay, roughly.
Probably, I'll add to that. The sun goes on the mirror. Some of them is reflected, some of them absorbed, and also when you throw the light onto the tower, some of them miss the tower, and the mirrors also get shadowed. So effectively, you get 60% of what goes on the mirror hitting the tower, but because the tower gets very hot, and another 20% actually loss in heat loss, and so only 40% actually go into the water.
That was a better explanation than mine.
Does the management ever mention about listing on the stock exchange?
Yeah, they've talked about it many times. I don't necessarily know the answer to that question. We've been involved in conversations with them about it, and it will be a decision for them a little bit further down the track. I suspect that they'll want to wait until some of these projects are a bit more mature than what they are right now. I think, you know, this Port Augusta facility is probably the most mature that they've got, and even at that, they're really now just starting to hit the ground and starting to get things off and running the way they need to be. If you look at what they're doing in the States and you look at what they're doing in Portugal, they're only really now getting into commissioning. So I suspect you find, give them another year when they're up and running and they've got some pretty substantial facilities up and running, they'll be worth an awful lot more than what they are right now, and it'll be at that point that they'll float.
Have you a ballpark figure for the total cost of construction?
$150 million was roughly the cost, yeah.
Can I ask the second question? When they are exporting electricity, do you know what price they get for it? Do they take advantage of the fluctuations in price, or is it a standard contract and all that?
I honestly don't know. Some stuff they don't tell us. Sorry, go.
I had a question about the saltwater cooling system and going through those baffles. And what happens to the salt, and how does that work with insecticides?
Through the cardboard you were talking about?
Yeah. So does the cardboard get replaced?
Yeah,
with salt?
Yeah, they have to wash them. Basically, they need to wash those cardboards from time to time and replace them as well. And Sundrop actually has an experimental rig in Port Augusta that they tried quite a lot of that technology to try to prevent it. And yeah.
What's the operating temperature up in the tower, and what's your peak storage temperature in the tank?
The boiler runs the turbine only 180 Celsius. So yeah, the turbine only runs at 180. The turbine only runs at 180 Celsius. So it's actually low efficiency turbine. I think it's 11%, something like that. And the temperature stored in the thermocline tank is 95 Celsius maximum. And so just make it doesn't need to pressurize the tank, and it can drive the multi-effect distillation basically.
Why did they choose the heliostat system? Because there are other technologies like Fresnel, lands like a trough system. Was it more efficient?
They did look at various things, and as you say, parabolic trough was actually one of the original design, but the consideration is that you heard Mark mention there are 45 kilometers if you want to walk around the base, and equally there are kilometers of pipes to consider if you have a parabolic trough, and so the reliability of that compared to the tower, and I think that was the main reason that yeah.
Reverse osmosis is a pretty energy efficient way of making water, and I was just wondering, although solar panels, photovoltaics are pretty inefficient, I was just wondering how it all balances out compared with solar thermal.
Yeah. Obviously what Sundrop get is heat, and well, you could probably use a PV to drive the reverse osmosis to generate electricity, but that is not actually the most efficient way to do it. And with multi-effect distillation, it's actually reasonably good, actually, in terms of if you get heat. And I'll probably try to explain the distillation process if you like. And if you imagine boiling water to make it spin into steam, and then you want to extract the fresh water again, you have to condense it. You have to extract all those heat. It's very energy inefficient if you don't do anything with that heat. But the multi-effect distillation is that it uses that heat to re-vaporize some other water and in the next chamber and so on. But each chamber get a reduced temperature. So you say the first chamber you vaporize water at 95 Celsius, then the second one might be about 70 and so on. So until that heat that you use to condense the steam in the first place is actually reused to generate more water. So it's actually quite an efficient process.
If the turbine is running, the boiler is running 150 Celsius, does it just use water as a working fluid, or does it use something fancy working fluids in the turbine?
Say again, sorry.
What is used as the working fluid in the
It's steam turbine. It's a steam turbine. Yeah, yeah, yeah. No, it's a steam turbine. Yeah.
Materials and labour. Do you know much about where materials were sourced and what local fabrication went on, or was a lot of it brought in as a sort of a ready-to-go construction?
The energy and water system was fabricated by Aalborg, as I understand, and shipped to Australia. So I think.
Things like the mirrors and the positioning system, that would have been brought in as well. Like I know mirrors are being, there's a very likely mirrors being designed in Adelaide, but that was well after Sundrop Farms commenced, and also tracking systems, I believe, are under development now.
Yeah. I think, yeah, beyond technical, that's I'm in danger of sort of trying to, but I believe the solar energy system was made by Aalborg and assembled in Port Augusta. Yeah. But, okay.
I think you find some of his fabrication was done here. So John Holland were engaged to be the EPCM contractor on this. So some of it's quite specialist stuff, so the heliostats, the tower, some of that specialist equipment, certainly the design for the greenhouses, as we've discussed, came from overseas. But a lot of the standard fabrication stuff was done right here. And John Holland engaged local contractors to do that more standard work.
So, following on from that process, are we going to see any of that stuff now built locally here or manufactured locally? Can that be done now, or would you be looking for that?
I think that's probably a broader question, and probably if we step outside of Sundrop world at the moment per se, the answer's got to be yes. We start looking at some of the solar thermal projects that are running throughout Australia, and we start looking at where they're sourcing their equipment. There's been a bit of a push locally to start being a little bit more in front of the game rather than reacting to what the rest of the world is doing. So there are a number of manufacturers now looking at being here, and there are a number of research agencies and companies that are looking at developing processes to create the mirrors and using different materials. And yeah, so yes is the simple answer. Yep.
Just a question about environmental assessments that have been made over time. Have they, what kind of checklist have they used to test the effect of the increased salinization in the region that they're returning the water to?
Yeah, good question. I think I was trying to, I guess, make the point earlier on that we've got to understand that the actual salinity of the water that's going back in is not much higher than the normal seawater. So from that perspective, it isn't such a big deal for the EPA. So they certainly made the right applications, and we put a bit of time and effort into calculating what that composition was going to look like. But just by virtue of the process, there is not really any chemicals being introduced into the system that would cause too many problems. Anthony probably knows more about it now.
Yeah. They did have an agreement with the EPA, and at 25 meters downstream of that exhaust, they cannot have salinity above a certain limit. I probably shouldn't say what the limit is, but there was an agreement, yeah, and they comply with that, yeah.
I just wondered if there's going to be more creations like this that are not just tomatoes but other crops that can grow in that kind of heat.
Yes. There is another project currently underway in South Australia, which you'll hear all about soon. Not allowed to talk about it. It was one of the stipulations.
Numerous insects, if I heard right.
Yes.
Why do you use them greenhouses?
Do you know? If I'm honest, that's the bit that we're not quite so familiar with. The horticultural side of it was done separately to the engineering work that we did. So what we do know is that they wanted to be sustainable. They wanted to be, at least to some extent, organic. They didn't want to be introducing lots of chemicals into the process, partly so that they could retain balance. So I'm not sure all of the reasons why they went down that particular path, other than to say that it remains true to the values that they set right at the very beginning. So I appreciate that probably doesn't quite answer your question, but that's our understanding of it.
I heard a rumour that they deliberately employ backpackers in the greenhouse because it's not good to work in there long term. Do you know if there's any truth to that?
Probably poorly qualified to make a comment there, really, but I don't know, just as an observation outside of that, I think the farming community employ backpackers for lots of different reasons. So, yeah, they may well be employing backpackers. I have a suspicion it's got more to do with the cost than it's got to do with any environmental concerns. Sorry, yeah. Go.
I think you said that all the tomatoes are sold to Coles.
Yes, there is a single offtake agreement. Coles, on review of the technical due diligence work that we did when we realised that this was going to work and give them a pretty steady stream of tomatoes, said, yep, we'll have that. Simple as that. So they take them all.
I find there's a bit of variety and taste in, vine ripened tomatoes, but I don't know where they all come from. Some taste better than others.
Yeah, so I think you need to remember as well, they're still ramping up, and it's about 15% of the total tomato production for Australia, so you aren't necessarily going to get Sundrop tomatoes just because. Yeah. Yeah.
You said they do some power management with what comes in from SA power networks, I'm assuming, and what happens on site, etc. And they balance that off against the costing of
Yeah.
software management, computer management,
Yeah.
and all that?
Yeah, absolutely. They've got some. So if you imagine a situation, I don't know if anyone's got solar power on their houses or any kind of turbines or anything like that, but if you have, you'll understand there's an inverter that manages when you're pulling power from solar, if you've got any batteries, when to store the power, when to be feeding back into the grid, when to be taking from the grid. It's virtually the same thing, just on a bigger scale.
And it's a lot more, like you can actually see what it's doing.
Oh yeah, absolutely.
Stuff we've got in our houses.
No, there's some pretty cool screens. Yeah. Yeah.
What happens to the organic waste?
That's a good question. I actually don't have the answer to that. I'm not sure. I don't know how much waste they're actually generating. I'm going to hazard a guess that they would recycle that and reintroduce it at some point. But yeah, I'm not too sure. Do you know?
No.
I reckon it's on the website somewhere. I'd be pretty confident. But yeah.
The subsequent projects in Portugal and the US, do you know if they've used any this design as the basis for theirs, and whether Frazer-Nash have been involved in either of those?
So the short answer to that, yes, we've been involved. No, it doesn't look the same. They've got all sorts of different solutions to the problem. So if we consider that the fundamental here is around generating heat, they're not so interested in where that heat's coming from as long as they've got a solution for that. So what we find is that they've done some work around looking at the waste streams from certain manufacturing type facilities and using that as an input into their heat requirements. We've talked a little bit about the fact that the heat we're talking about here isn't enormous. We're talking about 150 degrees C. That's in real manufacturing terms not actually that high. So it's quite surprising when you look around how many opportunities there are to harvest that heat from different places. So that's what they've looked at, as well as solar thermal and other things. But there's a bit of a mix there. Cool. I think we've run out.